Welcome to video 31.4. This is the fourth and last video about electromagnetic induction. And for this we're looking at RL circuits, which are a circuit composed of a battery, a resistor R, an inductor L, that's the circuit symbol for an inductor, and then we also have a switch that can go between either position A, where the battery is connected to the circuit, and position B, where the battery is not in the circuit. When the switch is moved to position A, current starts to flow. But the inductor opposes that current, and so the current doesn't instantaneously start. What happens is that the current gradually increases to a steady state value. And if we plot current versus time, what we'll get is a graph that looks about like that. The current starts out at 0, and then it gradually approaches the steady state value, which is equal to the EMF divided by the resistance, because in the steady state, the inductor basically just acts like a wire. After the switch has been closed a long time, I is equal to EMF divided by the resistance. When you move it to position B, other interesting things happen, but we're only going to consider for now the rising current. We'll look at the falling current later. And you might guess that mathematically this is going to behave a lot like an RC circuit, and you would be correct. Now to show that, we're going to write down Kirchhoff's loop rule, which is the EMF minus the voltage of the inductor minus the voltage across the resistor equals 0. And this is a differential equation. We're going to solve for I as a function of time. So what we'll end up with is di dt equals 1 over L times EMF minus IR. It's a separable equation, so we'll separate variables, and then we'll get di over EMF minus IR equals dt over L, except I'm going to bring the L back over here, and then we'll integrate both sides. Now, the integral on the right side is very easy. It's just time plus a constant. The integral on the left side, we have to use a u substitution. Use u equals E minus IR. du equals negative R times di. Using that, the left side integral turns into negative L over R times the integral du over u, and the right side is just the integral t plus some constant that I'll call C1. When you perform the integration, you end up with the natural log of u, which is EMF minus IR, and that equals negative R over L times T plus some other constant C2. C2 happens to equal negative R over L times C1. But since C1 was an undetermined constant anyway, the R and the L don't really matter. We can leave them off, just change the name of the constant to C2. At this point, we move up to the next column to get more space. We exponentiate both sides. That gives us E minus IR equals a third constant C3 times e to the negative R over L times T. And again, C3 we're going to define as e raised to the C2 power. And then a bit of algebra gives us I equals 1 over R times the EMF minus C3 e to the negative L, R over L times T. Next thing we have to do is we don't want that C3 there, we have to apply the initial conditions. And the initial condition is that I of 0 equals 0. So we'll set both T and I equal to 0. The result of this is that C3 happens to equal the EMF, and our solution, which is the current as a function of time, is equal to EMF divided by resistance times 1 minus e to the negative t over tau, where tau is called the time constant, and it equals L over R. And the time constant is defined in a similar way to the RC circuit, which is the amount of time that it takes for the current to reach 63% of its final value. The larger tau is, the more time it takes the circuit to come to a steady state. A small tau, it doesn't take much time. This is an equation that you may be called upon to solve in an AP exam. It's not that difficult. Even if you don't remember all the steps, you do need to memorize the equation for the rising current. And now we'll move the switch to position B. Remember, our circuit had our battery here. There's A, there's B, there's our resistor, there's our inductor, and now we'll get the battery out of it. Now remember, just before the switch was flipped, the EMF was at its steady state value, or the current was at its steady state value, and it's flowing that way. After the switch is flipped, the current is going to keep flowing because the inductor does not want the current to change. But since there's no more energy input into the circuit, it will eventually fall off to 0. I'm not going to solve the equation for you, I will set it up. This time we have IR minus L di dt equals 0. It's a similar differential equation to the last one, but because the battery's not in it, you don't need to do change of variables, and it's a little bit easier to solve. You should do that on your own. The solution you should get is I as a function of t equals e over r times e to the negative t over tau, where tau is defined in the same way it was before as L divided by R. If you graph it as a function of time, the current asymptotically approaches 0, and the initial value is E over R. The time it takes to fall by 63% is the time constant. So 0.37 of E over R. The time when it gets there is the time constant tau. Now an example here, this is problem 49 in your textbook. You've got a solenoid, it has an inductance of 6.3 microhenries, that's actually a relatively large inductance, and it's connected in series with a 1.2 kilo ohm resistor. A 14 volt battery is switched across the pair. The question is, how long will the current take to reach 80% of its final value? Well, remember the equation for rising current in an inductor is I of t equals E over R times 1 minus e to the negative t over tau. The final value of the current, though, is E over R. And so the result is that we can take the current equals the final value, I naught, minus e to the negative t over tau. And we want to find the time to reach 80% of it, so I of t will be 0.8 I naught And we have to do quite a large amount of algebra here. But you end up with t over tau equals negative natural log of 1 minus 0.8. And therefore, that t equals 1.61 times the time constant, which is 1.61 times L over R. Plugging in the values for L and R. L is 0.006, not 0.0063, but 6.3 times 10 to the minus 6 henries. The resistance is 1200 ohms. And the time equals 8.45 nanoseconds. So normally these circuits, the current rises very, very quickly unless the inductance is really, really large. And now we ask, what is the current through the resistor at time t equals tau? So we're looking for I of tau, and so we'll get the EMF, which is 14 volts divided by the resistance, 1200 ohms, times 1 minus e to the negative tau over tau. That works out to be 14 volts over 1200 ohms times 1 minus e to the negative 1 is 0.63. And the current at that time is 7.37 milliamperes. And keep in mind the time constant is something like 6 nanoseconds, so it doesn't take very long to rise to its final value. Tomorrow I'm going to check questions 7 through 10. And also please do try to solve the differential equation for falling current in an RL circuit.